So hopefully everyone is excellent. Let's see. So just a couple of reminders. And for now, I'm just going to mute all. But again, if anyone has questions, unmute yourself. Okie doke. So the first assignment is up, and the due date, if I recall correctly, was due next Wednesday, and then we'll take it up next Thursday. I think that sounds right. So today we're going to move on to chapter 2, which is decimals and percentages. So let's bring that up. Okay, so 2.1, Introduction to Decimals. This one definitely isn't too bad. There's like a couple of little questions about decimals, and then the main thing is learning how to round decimals, which you guys have probably already learned in other classes, but we'll go through it regardless. Okay, so still sharing, still recording, good. Let's jump in. So what the heck are decimals? I'm assuming everyone's heard of decimals. They're, of course, a way of writing numbers, basically a different way of writing a fraction. And place values are very important when it comes to decimals. So our number system is actually based on the number 10, and that stems from the fact that we have 10 fingers. As far as I know, that was basically the only logic that they originally used. Yeah, I mean, our number system definitely goes back a long ways. There were other number systems that actually had different base numbers. Now, of course, when we say that our number system has a base of 10, it basically means that there's 10 symbols that we use for our numbers, and then we just repeat after that. Like you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then after that, you don't have any new symbols. You just start to kind of reuse them. So it's based on 10. But other ones were based, for example, the Babylonian number system was based on 60. I think that's why 60 is a common number pretty much everywhere, because you got like 60 seconds in a minute. You got 365 days in a year, which is close to 360. A lot of the reasons 60 appears commonly in numbers is just because of the Babylonian number system. And then they have other proposed number systems for our system. Like, for example, a lot of people argue that 12 would be a better base than 10 because 12 has a lot of factors and a lot of divisors. So that's kind of a summary of our little decimal system. So here's an example. Okay, so as we move to the left, each position gets 10 times larger. So the 7 just represents 7 ones. So that's just 7. The 2 represents 2 tens. So that part technically represents 20. And then the 3 is in the hundreds category. So that technically represents 300. So that's why you got 327. So as you go to the left, every column represents a number that is 10 times larger. It's actually a very, I was going to say a brilliant way of doing it, but it's hard to imagine a different way of doing it, despite the fact that at one point in history, we didn't have a system like this. But yeah, it's hard to imagine what it would be like without a system like this. Yeah, it's like one of those things. Okay, let's keep going. Okay, so moving to the right of the decimal place, it's the opposite of moving to the left in the sense that everything is 10 times smaller. So the first number past the decimal point represents tenths. So the 4 in here represents 4 tenths. And then if you were to go to the further to the right, it would be hundredths. So if there was an 8 there, it would be 8 hundredths. So each number there represents a smaller and smaller value compared to the numbers to the left of it. They're 10 times smaller to be exact. What else do we have? So here's another good illustration. So the 1 on the furthest on the left is just represents the tens. So that's 10, and then the 7 represents the ones. So that's just 7. And then the 5 is 5 tenths. The 9 is 9 hundredths, and then the 1 is 1 thousandth. So that represents 17 and 591 10 thousandths. Yeah, so pretty straightforward, but a pretty clever way of doing it. Okay, so now we go to a couple of different types of questions. These ones are pretty straightforward, but these are the ones that everyone always forgets. There's always those questions like, dividing fractions, everyone always forgets those. And for these ones, I've seen tests where not a single person can remember the following types of questions, because they're, like I said, pretty straightforward, and it leaves people's brains really quickly. But let's do a couple of these. They are converting decimals to fractions. And the best way is just to start with some examples. Hold on, my mic's irritating me. Okay, whatever. Okay, so let's convert 0.123 to a fraction. So what you do is you count how many decimal places you have in each of these. So this goes to 1 decimal place. And of course, I mean to the right of the decimal point, 2 decimal places and 3 decimal places. So what you do for your fraction is, for the bottom number, you put 1 with 3 zeros after it. And the number of zeros is always dictated by how many decimal points the number happens to have. Because in this case, 0.123 technically represents 123 thousandths. So it makes sense to have 1,000 on the bottom of your fraction. And then the top part is even easier. You just write the actual number, just the actual digits. So just 1, 2, 3. So you get 123 over 1,000, and that's how you convert it to a fraction. So the top number is always just writing the actual digits, just as standard whole numbers. And then the bottom number is counting how many decimal places you have and using a multiple of 10 that corresponds with that. So you'll get either 10 or 1,000, or 10 or 100 or 1,000, 10,000, etc., depending on how many decimal places your decimal goes. Let's do a couple other ones. Convert 0.5643 to a fraction. So for this one, for the top number, you'll get 5643. That's all you do for the top. And then for the bottom, it goes, so you got tens, hundreds, thousands, 10,000s. So you could do it that way. You could just, you could do it that way and just write 10,000. Another way would be to just count how many places there are, 1, 2, 3, 4, and just make sure there's 4 zeros at the end of your number. So it's like tomato, tomato in regard to those 2 slightly different ways of looking at it. Just do whatever works for you. Okay, so that one, let's look at, so yeah, these don't really change all that much. They're pretty easy. And let's see what else we have. So in the next slide, we have kind of a general summary of what to do for these questions. Count how many decimal places the number has, and whatever place value this represents, use that as your denominator. Oh, someone raised their hand. Go ahead if you want to use your mic.
I just have a quick question.
Sure.
That'll probably get answered later in the slideshow. But what do we do for like those decimals that are like infinites, like infinite 6 or so?
Oh, what would you do for an infinitely repeating decimal if you wanted to convert it to a fraction? What a good question. That's a tough one. No one's ever asked that before, because of course, infinitely repeating decimals, they can be represented as fractions. Like for example, the example you gave, 2 over 3 is equal to 0.66666, and it repeats forever. But for converting from a repeating to a decimal, that's a tough one. I don't know off the top of my head. Does anyone have any ideas? I am curious now.
Infinite? Like isn't that kind of infinity?
Yeah.
Because there's no real fraction?
Well, in this case, so this is a repeating decimal, so it does have a fractional representation. Like another example would be 1 over 3. That does go on forever. That's 0.3333. Those can have fraction representations. Those are okay. What wouldn't have a fraction representation would be an irrational number that doesn't repeat. So that would be a number like pi, which is just a number that just keeps going on forever and it never even has an overall repeating pattern. That would have no fractional representation. So I guess the minimal answer I can give is that they do have fraction representations. I'm not exactly sure how you would find them. So out of curiosity, I'm going to go to Google and see what the answer would be, because that's a really good question. How to convert a repeating decimal into a fraction. Let's see. That looks complicated. Okay, I'm going to watch a YouTube video regarding that over the break. And then if it's an easy answer, I'll answer it. But if it's beyond the scope, I'll just skip over it. But very interesting question. I like the question. Let's see. Darn it, let's new share. Where was I here? Come on. Okay, let's see. So let's do this one. And geez, that question's going to drive me crazy. But I don't want to take up too much time on it. Okay, so let's do this one. So what would we get for 0.12? Maybe someone, type it out in the chat or jump in with your mic.
12 over 100.
Yep, exactly. Because in this case, we go to 1, 2 decimal places. So we got 2 zeros on the bottom, perfect. And then 12 is just on the top. Okay, let's see. Convert 0.007 to a fraction. Okay, so in this case, we have 1, 2, 3 decimal places. Some of them are 0, but that doesn't matter. Because the 7 is still in the far right of our number. So our method still applies. So it looks like we're going to have 3 zeros on the bottom, 1, 2, 3, and then a 7 on top. So 7 over 1,000. And let me just try to think of any common mistakes that people make in this case. Here's one common mistake that I see. Sometimes people will write the answer as 0.7 over 1,000. And that is, let me correct that. They'll write it as 0.007 over 1,000. So that's one mistake. Some people mistakenly will write the original number on top, when in reality, you just write the actual digits and you just write them as whole numbers. Because like this number right here is not the same as itself divided by 1,000, because that doesn't make sense. But it is the same as 7 divided by 1,000. So you always just use the actual digits on top. So that's one mistake. I'm trying to think of any other ones, but it seems like mistakes would be limited in this case. That's all I can think of for now. And let's see what else we have. So this one is a little bit different. It is a mixed number that we want to convert into a fraction. In this case, we just kind of use the easiest method we could possibly think of. For the 23, we just keep it as 23. So that part it almost feels like cheating, but that's what we do. So we keep that part as 23, and then we just convert 0.13 to a fraction. So that would be similar to the previous one, it would be 13 over 100. So we just write it as a mixed number. There is another way of writing this. You could extend it so that you could just write it as 2313 over 100. And that would also technically be the same thing. Some people write it as that, and I'll give them full marks because it's the same thing. Because like within this number, you have a 2300, and 2300 divided by 100 is indeed 23. So it ends up being the exact same thing. I would probably just stick with this method to avoid confusion. I would just write it as a mixed number. What else do we have? So here's another mixed number. So of course the 100 just stays as 100. And then the 5 is just at the 10th decimal place. So that would be 5/10, 5 over 10. And in that case, I would want the student to reduce that because the 5 over 10 part is reducible. it reduces to 1/2. So this would be 100 and 1/2. Okay, very good. So there's a bunch of other examples, but I think everyone probably gets the point. So here's a bunch of other ones. The answers are included. I'll let everyone just use these for practice for now. But in the meantime, let's see what else we have. Let's see. Okay, and then the next one is converting from fractions to decimals. So in this case, the answer is pretty easy. It is use a calculator. Take the top, divide it by the bottom, and see what you get. So in this case, all we're really concerned about in that regard is just different ways of rounding your answer. So let's take a look at that. And I thought there was, hold on, I thought there was another slide here. That's not cool. Okay, I want to discuss something else for a minute. So when you do, let's say you have, let's look at some fractions and let's convert them to decimals, and let's look at the different ones that you can get. One thing that you can get is like a decimal that just completely terminates, like 1 divided by 2. 1 divided by 2 equals 0.5. So you could get something like that where it's just a completely terminating decimal. You can get one that goes on for like a little bit longer in regard to its decimals. Like one example would be, let me try to find one that's finite. Oh, I hate this calculator. It always gives me fractions as answers. Okay, that's annoying. I guess I got my phone.
Sounds like you have a sharp right view, EL 5 something something something.
You are 100% right. That's what it says, sharp ELW535. So is this calculator notorious for being horrible?
I love it. It's like almost like a graphing calculator.
Oh, you like the calculator. Okay, maybe it's only just one mode function thing I have to fix in order to.
Yeah, you just keep hitting change and it will change it to a decimal for you.
Let's see. Okay, I'll try to figure that out later. Let's see what else we have. Actually, I have, yeah, sorry, I was under the impression that there was another slide in this. I guess that's in my pre-health class. I'm just going to grab it actually, because I have everything right here. Basic arithmetic. Decimals. And then we'll talk about pi for a minute, because pi is a super, super, super fascinating number, actually. There's even a pi day. Just give me a second, sorry. Here we go, here we go. Okay. So yeah, a couple of different options that you could get. In this case, this was the simplest one I could think of. Another one would be, let's say if you had 9/10. So you do 9 divided by 10, or sorry, 9/8. You do 9 divided by 8, and you get 1.125. So sometimes your decimals might go for a little bit longer, but they'll terminate. So there's a bunch of different variety of answers you can get in this case. And the point of going through all of these is just to illustrate that rounding is going to be an important skill to learn. And then like we illustrated before, some fractions can have infinitely repeating decimals. So for example, 1/3 is equal to 0.333, etc. And then it just keeps going. So to denote a repeating decimal, there's some notation that you can use that's very convenient. Obviously, you can't write out, infinitely many threes, but you can write it. So there's a couple different symbols. You could write 0.3 with a dot above it, or you could write 0.3 with a bar above it. And that's just an easy way of letting the reader know that that digit repeats forever. Yeah, but don't overuse that notation, because sometimes I see people using that in numbers that aren't even repeating decimals. You only have to use that notation if it's a repeating decimal. And if you've taken that repeating decimal and rounded it, then you no longer have to use the notation because it's no longer a repeating decimal. And then you have numbers that can't be represented by fractions, like the number pi. You could come up with fractional approximations for pi, but you can't come up with an exact number for pi. So pi is very interesting. It is what is the definition of pi? I remember that's like such basic geometry that it was like 10 years ago. It is the ratio of the circumference of a circle to its diameter, I think. And it creates the same number for any circle, 3.14159, et cetera, because that's all of pi that I have memorized. And pi is really interesting. So for example, because it repeats forever because it goes on forever and never repeats, any given string of numbers exists inside of pi somewhere. So all of your phone numbers are guaranteed to be in there, all of your addresses. If you roll the dice 1 billion times and you got a really, really unique string of numbers, even that number would be guaranteed to be in pi. So pi is very fascinating. People have been studying it since antiquity, which would be like 2,000 years ago. Archimedes came up with approximations for pi. He was really smart. Euler came up with approximations. There was a mathematician called Ramanujan who came up with like the weirdest, most confusing, most freakish looking formulas to approximate pi. So yeah, pi is very, oh, and here's another thing that you could actually do, that you could try. There's something called the hot dog pie throwing game, which sounds definitely weird, but let me explain it. I just want to bring up the website I usually go to so that I don't misstate it. Hot dog pie throwing, I'll just put hot dog pie game. Here we go. So this is pretty neat. This is a game where you basically buy a bunch of hot dogs and you put them in your freezer, and then you set up an area on your floor that has, like, you can use duct tape, and you set up a bunch of parallel lines on your floor. And each of them has to be the same width away from each other as is the length of a hot dog. And then what you do is you take your hot dogs and you toss them into this area, and you record how many tosses in general you have. So you'll have your number of tosses. And then when a hot dog lands and crosses one of the lines, here's your hot dog, then that counts as a cross. And you keep track of these two numbers. And then if you do this enough with hundreds and hundreds of hot dogs, you'll actually start to get an approximation of pi just by the fact that you're throwing hot dogs on the ground. You'll actually be able to tabulate your tosses, tabulate your crosses, and you can use a formula that will give you an approximation for pi. And the formula would be, the website says, it would be 2 divided by the number of crosses times the number of tosses. And that'll actually give you a number close to pi. And if you keep doing this thousands of times, you can get a pretty accurate number. And if you did it infinitely many times, hypothetically, you would get arbitrarily close to pi. So that's how prevalent some numbers are, even irrational numbers, that just literally throwing something has pi built into it, just for whatever reason. I don't know why in this case. I guess that's more of a philosophical question, or maybe I just haven't looked it up. But yeah, it's a fascinating game. And another number that is really cool, and then we'll return to the lesson. Sorry for my rants. There's a number called phi, which is another kind of famous irrational number. Phi is a particular Greek letter. And phi basically appears absolutely everywhere in nature. You can't get away from it. Like, here's one weird example. People who we find attractive have phi built into the ratios of their face. So Leonardo da Vinci, when he drew the Mona Lisa, he actually used phi to make her more aesthetically pleasing. So he used mathematics to make his art more beautiful. And we have it built into our bones in various ratios in our body. It's in any spiral. So every time you smoke a cigarette and you see a spiral, that is dictated by this number phi. Even the spiraling of galaxies can be mapped out using this number phi. I also read that it's present in our brain waves as well, and the way our brain functions. So yeah, these numbers are, it's almost weird how they're just like all over the place, and it's, yeah, it's very interesting. What else is there about phi that's interesting? There's a ton. There's an interesting movie called Pi by Darren Aronofsky. It was an independent film he made many years ago, and that's an interesting movie. It has a lot of cool math stuff in it. Okay, so that was a fun rant on various things. Now let's go to, so all of that, the reason I was kind of showing that is that you're going to have to learn to round, because you know you can get a variety of different answers in regard to their decimal places, and sometimes you want an answer to be a bit more manageable, especially if it's like an infinitely repeating decimal place. It's like, what the heck are you going to do with that? And oh, actually, hold on. There's one more side rant I want to do, and then we'll do some rounding exercises. But this is something that my teachers taught me in university. And at first we didn't believe them, but yeah, it's actually true that 0.9999, and it goes on forever, is literally equal to 1. And most people are like, no, it isn't, but it actually is. I've looked up proofs of it, because infinity is different from kind of everyday logic. So in this case, even though it doesn't look like the same number, if the decimals went on forever, it would be literally equal to 1. And the proof of that is actually really, like, surprisingly, shockingly easy. Let's think about this for a second. Just give me 2 seconds to think about this. Let's see, we could do, so let's try to start with 0.9999, etc. And let's try to get it equal to 1 by using legitimate mathematical manipulation. So let's write this as 3 times 0.3333, etc. And then it still goes on forever. So it's still the same number. And then what we can do is take this part and write it as a fraction, because it's just equal to 1/3. So you get 3 times 1/3, and 3 times 1/3, ta-da, is equal to 1. So indeed, 0.99999 going on forever literally does equal 1. It might just be a bit of a flaw in the way that our math system is set up, or maybe it does make sense. Who knows? I think there would be various opinions on whether or not this intuitively makes sense or not. But I just thought it was a fun fact. Okay, I keep getting distracted. Apologies. Okay, so being able to round is very important. The point of rounding is that you are making your number more manageable by kind of dropping off some decimal points, but you also want to keep your number as close as possible to what it was in order to avoid accuracy or losing accuracy. Let's see, so here is just a basic example using whole numbers. Let's say that you had 73 and they wanted you to round, whoever they are, they wanted you to round to the nearest tens. So they want you to either round down to 70 or round up to 80. And you got to figure out, well, which one's closest to the original number. So of course, for 73, you would just round down to 70. On the other hand, if you had 76, then 76 is definitely closer to 80 than it is to 70. So in that case, you would actually round up to 80. So you're changing the number, but keeping it as close as possible to what it previously was. Sorry, give me a second. Apologies. Okay. So let's keep going. Let's look at some rounding for, oh, and here's the actual procedure for rounding, and then we'll look at some examples. Okay, so first you'll be told which is the last digit that you're keeping. So like the question will have to specify to you, you know, round to 2 decimal places, round to 3 decimal places. So that part has to be specified to you. So basically what you do, if your number is 5 or above, you round up. If your number is 4 or below, you round down. So that was just what they decided with. So 4 or below, you go down. 5 or up, you round up. And I think the best way is to look at some examples. Let's round 0.23 to the first decimal place. So 0.23. So the first decimal place is 2. So what you do is you look one place to the right of that. So whatever it's specifying to you, you always look one to the right of that. You look at the 3, and the 3 is the digit that tells you if you should round up or down. So in this case, it's 3, it's less than 4, or sorry, less than 5, so you round down. So what you do is you just drop that 3 and you get 0.2. And you've officially rounded to your first decimal place. So if it tells you to round to the first, you always look at the second and then you know what to do. So that's one example of rounding down. What about another one? So this one will be an example of rounding up. So let's say you have 0.27. Oh, let's see the chat. Someone asked, is this on iLearn for the stuff I missed? Yeah, all of this was on iLearn, yeah. And then the recording will be on my YouTube channel, so you can see the actual lesson if you want as well. And the link is in news on iLearn. And actually, I'm just gonna make sure that we're still recording because I'm always paranoid that it's gonna stop because sometimes it does. Okay, still recording. Okay, so 0.27, it still says round to the first decimal. So it wants you to round so that you only have one decimal past the decimal point. So what you actually have to look at is this number right here. It's a 7, as far as I can tell. So in this case, you would round up. So rounding up is you drop the 7 and then you increase the 2 by 1 digit. It's basically the equivalent of taking 27 and rounding it up to 30. That's like the logic that it uses. So 7 drops and the 2 increases by 1. So those are the only 2 cases. When you're rounding down, you just drop the appropriate digits and then everything else just stays the same. When you're rounding up, you drop the appropriate digits and then you increase the immediate leftward digit by 1. So let's go through a couple more. Round 0.479 to the second decimal place. So yeah, you always got to be careful because like it could say first decimal place, it could say second, it could say third. Sometimes it might state it a little bit differently. It might say round to the tenths decimal place or the hundredths or the thousandths. And those of course are just referring to the first decimal place, the second, the third. So there's different ways of wording this. Oh, someone said just checked the content section and it's not there. Oh, you might be right because this is chapter 2. I might have forgot to post it. Thank you for letting me know. I'll definitely post it after class. Sorry about that. Okay, oh, hold on, let's see. Okay, sorry about that, everyone. I will, yeah, I'll post that. So for this one, 0.479, let's write that down. 479. So round to the second decimal place. So this one right here, you're going to round to that one, but the one that you look at is that one. And of course, you'll be rounding up because it's a 9. Stupid fruit flies, get away. So this will round up to 0.48. So just like I said, the 9 drops off and then the next digit just increases by 1. Yeah, and again, the logic of this is that it's the equivalent of, it would be the equivalent of having 479 and rounding to 480. That's the logic that you would, that it pretty much uses. Okay, let's do this one. 0.34. Darn it, I hate this thing, 0.3451. Round to the third decimal place. So fifth is at the third decimal place, or 5, I should say. And to the right of that is 1. So that 1 is just going to drop and everything else will just stay the same because we're rounding down. So, you know, like I said, I think everyone's probably seen this, especially regarding the considering the program you're in, but be sure to practice them because, you know, if you practice them, they're very easy. It's pretty much free marks. Yeah, just read the question carefully, whether it's second or third or fourth or whatnot. Okay, let's do, so there's a bunch of examples. We'll do one page of these and then we'll leave the rest for practice. Here's a couple. Round the following numbers to the second decimal place. Why doesn't everyone answer in the chat? So what would we do for this one? What would be our answer?
$6.60. I mean, 80. Oh, wait, no, 76 to 80. Yeah.
In this case, so second decimal place is this one right here, right? So we're going to be looking at this one to know what to do.
6.58.
Yep. So you would drop that and then just increase the 7 by 1. So you have to remember that when you drop your appropriate numbers, you're only changing the one that's to the immediate left of them. Yeah, sometimes people will change other numbers, like they'll change the 6 or the 5, but in this case, the 7 is the only thing that's going to be changing. Let's do the next one. So next one, same thing, round to second decimal place. So what do we think for this one? Oh, someone said, let's check the chat. 10.14, yes. Good. In that case, we rounded up because there was that 8. In this case, there's a 4 right there, so we'll round down. Those are the easiest cases because you just ignore the 4 and just write everything else the same. And then the last one, you have a 1. Actually, here, I'll see if anyone.
So it'll be 2.887.
Yeah, 2.87, exactly. 2.87. Good. So that is it for this particular lesson. And then there's a bunch of links on decimals, converting from decimals to fractions, articles on rounding, check those out. And then there's stuff under additional material, which will be posted. Okay, let's just take a 10-minute break, and then we'll continue. So everyone come back at 4:20. The recording. Okay. Oh, a couple of people were just messaging me asking about the assignment. How do we submit it if all the classes are going to be online for the next week or two? So just submit it on Dropbox. Hopefully I activated that. If I hadn't, I'm surprised because usually I do it right away. So submit it on Dropbox. You could just take pictures of your assignment. Oh, someone said I did. Okay, perfect. So you can either take pictures of them as long as I can see your work, because some pictures are really poorly done. So take nice clear pictures, or if you have a scanner, you can scan it and upload it as a PDF. So that's yeah, we'll do it that way. And that's funny. Someone made a funny joke. They said he has opened his third eye. That's funny because third eye in symbolism is often referred to higher enlightenment or spirituality. So I like your joke. It's funny. Okay, let's. Oh, is there a screen recording for what I missed earlier? Yeah, it'll all be on YouTube. Yeah, and the link is in news on iLearn. Okie doke. Let's keep going. Recording is still good. Okay, so this is 2.2, adding and subtracting fractions. I have to admit, I was surprised that this is in the course.
Decimals?
Oh, sorry?
You said adding and subtracting fractions, and you said decimals.
Yes, sorry about that. Yeah, I'm a bit tired. Yeah, exactly. So 2.2, adding and subtracting decimals. So this is pretty much just like what we did in grade school. So I don't have a whole lot to say about adding and subtracting fractions as a concept in general, but we'll go through some methods and we'll look at some examples, and it's pretty straightforward. And then later on, we'll do multiplication. And then I'm on the fence if we're going to do long division, because it's long division. I will make a judgment on that soon enough. So maybe we'll just go to just a whiteboard for this one. Darn it, my laptop. Sorry, I need to grab my laptop if I'm going to use a whiteboard, because I was going to post stuff, but then Buddy was, I had to clean his cage. Give me 2 seconds. I'm back. Okay. Whiteboard, Buddy, go back on my shoulder. Enjoy. Okay. Let's see. So stop sharing. Go to a whiteboard. Okay. So the first one is just adding 2 decimal numbers. So let's look at this one. 1.23 plus 4.56. So basically you set this up in kind of a vertical way. Most people probably at least vaguely remember this from probably elementary school, which is where you just do 1.23, and then you have a plus sign, and then you have the number below that, so that you can kind of add them column by column and make sure that they line up, and make sure that the decimal point lines up with as well. And then you add them, not surprisingly. So 3 plus 6, and you just go column by column by column. So 3 plus 6 is 9. 2 plus 5 is 7. A decimal place is a decimal place. And 1 plus 4 is 5. So hopefully my math is right on that. And that's 5.79. So that's like the simplest possible case. That's the case where you don't have to do any, what the heck is it called? Oh, I can't believe I forgot what it was called. Carrying over. You don't have to do any carrying over in this particular case. We'll look at those cases in a minute. Let's see what else there is. Okay, so there's one more. Well, there's a lot more, but there's one more on this particular slide. So this is 1.41 plus 5.22 plus 3.13. So let's line all of these up. 1.41 plus 5.22 plus 3.13. Okay, and then now so 1 plus 2 plus 3 is 6. And if I make a mistake, let me know, because like I mentioned, I'm just bad at adding stuff and subtracting stuff. 6 plus 4 plus 2 plus, so that's 7. Decimal point sits there, and then 1 plus 5 plus 3 is 9. So you get 9.76 for that one. So those are the most straightforward cases. It's so nice having Buddy on my shoulder, because he was just under his heat lamp, so he's like really, really hot, and it's like it's nice. Thanks for warming me up, Buddy. Okay, so here's the general procedure for adding fractions. Line up the decimal point, add the correct place values. So like I said, you do it kind of column by column. So tenths by tenths, add those up, add the hundredths, add the thousandths, add the tens, add the ones, add the tens, add the hundreds, all that stuff. Just make sure it all corresponds with what it's supposed to. And you could use zeros as placeholders if you want. We'll see a specific example of that just to illustrate what that means. And you may have to carry digits if a column adds up to more than 10. Yeah, so that ends up being an issue. If you have a column, it adds up more than 10, and you can't really put like a 10 or 11 or 12 in here because it messes things up. So you got to do something called carrying the digit, which we'll also look at examples of. So let's see what is next. Yes. So the next one is an example of where you can use zeros as placeholders. So you got 13.2 plus 1.57. So let's write this as 13.2, and then you got 1.57. Notice that what you line up is the decimal point. That's what you line up. And in this case, this looks a bit weird because you have one that goes to 1 decimal point, you have one that goes to 2. So just add a 0 right here, and then it looks less weird. And it's exactly the same as what it was. And then everything is perfectly lined up, including the decimal point. And now let's do this one. So 0 plus 7 is 7. 2 plus 5 is 7. A decimal and a decimal is a decimal point. And then 13 plus 1 is 14. So 14.77 for that one. So I'll try not to do like a million of these because, I mean, yeah, they're not going to change all that much. Let me try to find ones that have some type of uniqueness in them. Let's do the bottom right one on page 4 of the slides. I'll just get rid of this. So this one is 0.07 plus 6.79 plus 0.3 plus 3. So let's just do it in order. So 0.07, good. And then below that is 6.79, 6.79. Again, always line up the decimal place so that your columns are lined up. I think columns is the right word. Yeah, columns are vertical, yes. And then 0.3 we'll write as 0.30, just so it kind of looks a bit better. And then for 3, we'll write it as 3.00. Again, just so there's no like weird gaps in our tower of numbers. Yeah, you could always add zeros like that into a number and it doesn't change it. Oh, in this case, it looks like we also have to do some carrying of the digits. Is this? Yes. Okay, so if you look at the first column, you have 7 plus 9, which is 16. But if you just put 16 in here, it would kind of mess up the whole thing because then it's like it's crowding the next column and it just won't work. So what you do is you just take the ones part, which is the 6 of the 16, put a 6, and then you're kind of missing 10. So you just put a 1 up here because that's 10 times higher than what's to the right of it. So by putting a 1 there, you're basically transferring 10 times the original amount over into that column. So that's what you do when you have a number that's bigger than 10. You just write down the ones and then you just put a 1 up in the column to the left, or a 2 or a 3, depending on whatever you actually have. And now you keep going and you just kind of consider that a number in the column. 1 plus 7 plus 3 is 11. So here you got the same problem. So what you want to do is just put the ones part there, and then you put the 1 right there, and then you just keep going. And then 1 plus 6 plus 3 is, what is that, 10. So in this case, and let's put the decimal right here, in this case, you could just write 10. So that's how you carry digits. So yeah, it's not too bad. And I think some people would probably make the mistake of writing like a 10 up here rather than a 1. But again, because our decimal system is already based on multiples of 10, you don't have to do that. You just add a 1 and it works because that column already represents something particular. What else is there? Why do I have this one? Okay, so this one's a bit more of a here. Maybe we'll go back to these slides just for a second. And let's look at this one's similar, but it's kind of, you got the steps included in the lesson. So it's 1.54 plus 3.28. So you arrive at the same problem. 4 plus 8 is 12. So you just put the 2 in there, and then you put the 1 at the top. And then you add the next one. The next one is 8. So no worries there. That's just an 8. And then the rest of it is straightforward. Yeah. What else is there? I don't think there's too much else to say about adding decimals. There's a couple of other examples of carrying decimals over. So I think I'll leave those for everyone to practice. And if anyone wants to go over them next class, we can do that as well. But they look, yeah, they look all the same. And just like this one, all the little details are included. Okay, let's do subtracting decimals and then we will be finished. Okay, let's just go. Yeah, let's go back to the whiteboard. Get rid of this. Okay, so subtracting decimals is pretty much the same thing. There's only one difference, that in some cases, instead of carrying a number, you have to borrow a number, which is kind of like the reverse of carrying something. Like we'll look at examples, but first we'll look at the simplest possible ones. We got 437.56 minus 41. Okay, so let's write this in our fancy vertical form. So 437.56. And then for 41, make sure you line up the decimals. So I'm just going to draw the decimal right here. 41 is 41, and then you could put two zeros over there. Okay, and now let's subtract them. So we got 6 minus 0 is 0, 5 minus 0 is 5. Sorry, 6 minus 0 is 6. 5 minus 0 is 5. 7 minus 1 is, oh, here's the decimal, is 6. And then 43, in this case, let's see, what would be the best way of doing this? Yeah, you could just do 43 minus 4, which is 39, and you'll get the right answer. So that's what you do for those. So pretty much the same thing as previously. What else? What else? The next example is doesn't really add anything new. Let's see if there's anything else that's interesting. Okay, so I'm just going to read off the slide for a second. In some cases, you may need to use a technique called borrowing. Borrowing is used when the numbers in one of your rows is not high enough to subtract the next row. You may need to, quote, borrow some values from one column to another. And like I said, it's the opposite of carrying. And it's actually kind of a really neat, clever technique. It was something I totally forgot about. So let's do one. So this is 3.5 minus 1.7. I'll just write it in this form just to save time. So 3.5 minus 1.7, that's, you know, perfectly fine. You'll get a reasonable answer. But when you do it in this kind of placeholder type technique, you might run into a problem. There's kind of an obvious problem right off the bat right here, is that if you do 5 minus 7, you're going to get a negative number. And you shouldn't get a negative number, because like 3.5 minus 1.7 is just, it's some positive decimal number. So that's a problem right off the bat. So what you can do is you could actually take 10 from this. So let's cross this out and we'll put a 2. You've basically just stolen, or actually in this case, sorry, that's the ones column. So you can take 1 from there. So you've basically stolen 1 from that column, and you could just put it right in the rightward column and put it there. And then at least in this case, now you technically have 15 minus 7, and you could actually do it without getting a contradiction. And it's actually a valid way of doing it. You're basically taking from one column, putting it in another column. And keep in mind, each column to the right is 10 times smaller. So that's why in this case, you're technically only taking away 1 number from the 3. But in this case, you're adding 10 to your original 5, because the column to the right is 10 times smaller than the column to the left. So anyways, 15 minus 7 is that 8? Let's say it's 8. And then decimal point, and then 2 minus 1 is 1, and you get 1.8 as your answer. So it's kind of neat. As you can see, it's pretty much literally just the same, or the opposite as carrying a number. It's kind of just doing it like in reverse. So let's look at a few more of those, because Those ones are a bit unusual. Let's just do one over here. So this one is 8.35 minus 2.61. Okay, so for the first one, we're good to go. 5 minus 1 is 4. Good. For the next one, we got a bit of a problem. We got 3 minus 6, which would be a negative number. And if you did it that way, it would just absolutely not make any sense, because like, how could you have a negative number within a decimal? Like, you can't have a negative sign in the middle of a number. So in this case, let's take from the 8, change it to 7. So we've just taken 1 from that. And that becomes 10 in the next rightward column. So the 3 becomes 13. And then we're golden. 13 minus 6 is 7. Write your decimal point. And then 7 minus 2 is 5. And you get 5.74. So as long as you do it properly, you'll be good to go. Oh, and I guess that's it. So at the end of the lesson, check out the links. We got an article on adding decimals, subtracting decimals, and then it says there's a worksheet of hundreds of different questions that you could work on. And that's all on mathisfun.com. And I'll post all the chapter 2 stuff in a few minutes. Okay, so that was a solid lesson. Let's stop the sharing. Okay, so yeah, just to recap, first assignment due Wednesday, take it up Thursday. I'll post the second one early, just so it's up, and then I'll post all the chapter 2 stuff as well. Please submit your assignments on Dropbox. Does anyone have any other questions? Everyone seems pretty good. Okay, so I guess I will virtually see you next Wednesday, and of course I'll keep you updated on my results. And everyone have a great weekend. Thanks for coming.
I hope you get better, John.
Thanks.
Have a
Yeah,
good
get
one.
better soon.